In this assessment, we're asked to tell what fragment is responsible for the peak at 57. So we're looking for a peak that has 57 atomic mass units. The fact that it shows up in the mass spectrum tells us that this peak must have a positive charge, and we're given this structure here. So we can actually do this in one of two ways. We can think about how a molecule like this might fragment. So we're going to make that radical cation in the beginning, and it's going to fragment, and we could show a mechanism for that fragmentation, or we could simply use math. So we'll kind of do it in both ways. Knowing that the fragment is going to have a mass to charge ratio of 57, and it's going to have something that was present in this molecule, we can start to think about, well, how many carbons and how many hydrogens would add up to a mass of 57 atomic mass units. And so it turns out if we have 4 carbons, that's going to be a total of 48 atomic mass units. To get to 57 then, we would need only 9 hydrogens, which would give us another 9 atomic mass units for a total of 57. Now this C4H9 fragment should make us think about a tert-butyl group. And again, we're showing it with a positive charge because the fact that we see it in the mass spectrum tells us that it must have been a cation. Now, how could this have formed in terms of fragmentation? For that, we can draw an arrow pushing mechanism where the electrons move to here. That one electron, we assume that that radical cation is in this bond. One electron moves to here, and that would give us that tert-butyl cation. But the fact that the mass to charge ratio is 57 and this motif, this fragment appears in the molecule itself is enough to make us believe that that 57 corresponds to the tert-butyl cation.